In this lesson, we'll investigate the process of starting with a group under addition and then constructing a group under multiplication. We'll do this with Z10 first, and then we'll apply that same process to a matrix group. So let's see what happens. We'll start with Z10, so that's the set from 0 through 9, and recall that Z10 is a group under addition. But we know that we can not only add, but also multiply in Z10, which begs the question, is Z10 a group under multiplication? So if you could pause the video for a moment, see if you can answer that question. All right, well, let's go through the group properties. Again, we know that Z10 is a group under addition, and now we're going to check if it's also a group under multiplication. So, first, closure. Yes, under multiplication, Z10 is closed. If we have a pair of elements in Z10, multiply them together, the product is still in Z10. So closure under multiplication holds. What about the associative property? Yes, Z10, multiplication in Z10 is associative. We can move parentheses around and regroup when we're multiplying these numbers in Z10. What about the identity element? Well, here we're talking multiplication, and so the multiplicative identity is 1, which is in fact an element of Z10. The final group property, so far it's 3 out of 3, multiplicative inverses. And unfortunately, this is where the group property fails. For example, 0 element does not have a multiplicative inverse in Z10 because 0 times x equals 1 is not possible in Z10, and therefore 0 does not have a multiplicative inverse. And so unfortunately, Z10 is not a group under multiplication. So here's our dilemma. Z10, which is a group under addition, is not a group under multiplication because we just saw that not every element has a multiplicative inverse. The 0 element, for instance. Now here's another element of Z10 that doesn't have a multiplicative inverse, namely 4. 4 times x will never equal 1 in Z10, and therefore the multiplicative inverse of 4 doesn't exist in Z10. Now we do know that Z10 is a group under addition, and in fact the additive analog of 4x equals 1 is 4 plus x equal to 0 because we're adding, and also the identity element, the additive identity, is 0. This equation is possible in Z10. In fact, 6 does the job. And therefore, the additive inverse of 4 does exist, namely 6. And so there's a subtle notational difference here. 4 to the minus 1 stands for the multiplicative inverse of 4, which doesn't exist in Z10. Minus 4 stands for the additive inverse of 4, which does exist in Z10, namely 6. And so, once again, we have this dilemma where Z10 is not a group under multiplication. So what's the salvage? How can we salvage this situation? Well, what we've done in the past is we defined a subset of Z10, namely U10, which consists of elements in Z10 with multiplicative inverses. And we've seen from our past work that U10 contains the elements 1, 3, 7, and 9. 1 and 9 are self-inverses, and 3 and 7 multiply together to be 1, mod 10, and so 3 and 7 form an inverse pair. And so the first thing you'll do in today's classwork is verify that U10 is in fact a group under multiplication. And so that's the salvage we made, that we started off with Z10, which is an additive group, which was not a group under multiplication. And so we defined this subset, just holding on to the elements of Z10 that do have multiplicative inverses. Another way to think about it is toss out the elements that don't have multiplicative inverses, and what's left happens to be a group under multiplication. Again, you'll verify that right off the bat in today's classwork. Now, please pause the video and work on day 10 classwork. And afterwards, we'll go over some of the questions and concepts. Now let's turn our focus on a matrix group. So we'll let M of Z10 be the set of 2 by 2 matrices with entries in Z10. And remember that M of Z10 is a group under addition. However, we recall that we can not only add matrices, but we can multiply 2 by 2 matrices as well. In other words, we can add and multiply in M of Z10, which once again begs the question, is M of Z10 a group under multiplication? So, just as we did with Z10 in the beginning of class, let's go through the group properties and check whether M of Z10 is a group under multiplication. Well, starting with closure. Yes, M of Z10 is closed under multiplication. If we take a pair of 2 by 2 matrices, multiply them together, still a 2 by 2 matrix with entries in Z10. So closure is good. We recall that matrix multiplication is associative. We can move parentheses around, still get the same result. And so associativity is check. What about the identity element? Well, now we're talking multiplication here. And in fact, the multiplicative identity matrix is our epsilon matrix 1, 0, 0, 1. And that is an element of M of Z10. So we do have the multiplicative identity in M of Z10. But then we run into inverses once again. And as you saw in the classwork, for instance, that the matrix 2, 3, 0, 0 multiplied by any matrix will never equal 1, 0, 0, 1. In particular, this bottom row, if we multiply 2, 3, 0, 0 by any matrix, will always equal 0, 0. So this isn't possible. And therefore, 2, 3, 3, 0 does not have a multiplicative inverse. And therefore, not every element of M of Z10 has a multiplicative inverse. And unfortunately, it is not a group under multiplication. So we run into this dilemma once again, where M of Z10, while being a group under addition, is not a group under multiplication. So what's the salvage? Well, we define this subset called G of Z10, consisting of matrices in M of Z10 that have multiplicative inverses. In other words, we toss out the matrices without multiplicative inverses, and we're left with G of Z10. A couple of remarks about G of Z10. First, this is exactly like how we obtained U10 from Z10. The second remark is the use of the letter G here. This particular subset is often called the general linear group, and therefore the use of the letter G here. So we'll go through the argument. The claim here is that G of Z10 is a group under multiplication, just like U10 was a group under multiplication. So let's go through the argument. First, closure. G of Z10 is closed under multiplication, and the proof of this is very similar to the argument you made in the classwork for UM. And so I will leave it up to you to look at the proof that you did for UM being closed under multiplication and see if you can adapt it for G of Z10. We also know that matrix multiplication is associative, and so that property is satisfied. So we'll check off the first two properties. How about the identity element? Well, we know that under multiplication, the identity matrix is 1, 0, 0, 1. We also have to verify that that matrix is contained in G of Z10. And it is. Well, how do we know that any matrix is in G of Z10? Well, we have to verify that it has a multiplicative inverse. That's the defining property to be in G of Z10. Now, epsilon has a multiplicative inverse because it's a self-inverse. Epsilon times epsilon is epsilon. And so epsilon is in G of Z10. So that's a check. And how about the inverses? Well, so let's start with an arbitrary element of G of Z10. Now, our final goal is to show that not only its multiplicative inverse exists, but that it exists in G of Z10. So that's what we need to show. It's not enough to say, well, you know, any element of G of Z10 has a multiplicative inverse. That's the defining property. So that step tells us that alpha inverse does exist, but we have to show that alpha inverse exists in G of Z10. And so how do we argue that alpha inverse exists in G of Z10? Well, we have to show that alpha inverse has a multiplicative inverse, but it does. This relationship right here, alpha times alpha inverse is the identity, tells us that alpha is the multiplicative inverse of alpha inverse because they multiply together to be the identity. And therefore, alpha inverse has a multiplicative inverse, namely alpha, and therefore alpha inverse is an element of G of Z10. And so that takes care of the inverse property. And so just as we showed that U10 is a group under multiplication, G of Z10 is also a group under multiplication. And the argument is very similar to the one that you would make for U10. We'll end this lesson by highlighting one more similarity between U10 and G of Z10. Now, by definition, U10 contains numbers in Z10 that have multiplicative inverses. And G of Z10 contains matrices in M of Z10 with multiplicative inverses. And so multiplicative inverses is the defining property of both groups. However, each group has a trick that allows us to quite easily determine whether or not an element is in that group or not. So for example, with U35, we know that 8 is an element of U35 because 8 and 35 are relatively prime. Well, we may not even know right off the bat what the multiplicative inverse of 8 is, but we know that it exists because 8 and 35 are relatively prime. So that's the trick that I'm referring to. Conversely, 10 is not an element of U of 35. We could argue that 10 doesn't have a multiplicative inverse mod 35, but we can more easily see that 10 and 35 are not relatively prime. Their GCD is 5, not 1, and therefore 10 is not in U35. And so that's the trick with U35. How about matrices? What's the trick to determine whether a matrix has a multiplicative inverse or not? Well, that trick was the determinant. So alpha, for example, the matrix 2, 1, 5, 4, its determinant is 3, which is in U10, and therefore this matrix is in G of Z10. Whereas matrix beta, how do we know that it has a multiplicative inverse? Once again, the determinant. Its determinant is 8 minus 3 or 5, which is not in U10, and therefore we can conclude that beta doesn't have a multiplicative inverse and therefore not in G of Z10. So that's the trick with matrices. We look at its determinant, and that helps us determine whether or not it has a multiplicative inverse. So that's another similarity between U10 and G of Z10. And so that's the end of this lesson. We studied a lot about similarities between these kinds of groups. And I will see you next time.